Okay, so this is the last section in the chapter on integration, right? Change of variables. Um, it seems that this topic is fairly lengthy. I'm not sure if that's because of my explanations or if it's because the topic itself is um, involved. We'll see based on the length of this video, but you can see that my notes are a bit longer than usual. Um, so the first thing here, we're sort of defining this abstract idea of transforming one region into another region. And you can see that in this picture, the region in the UV plane is somewhat simpler to describe than the region in this XY plane. So, and you have like this region is called G and this region is called R, and this map, which would be called T, is a transformation. So planar just means that it's of two variables, basically. There's going to be a section later on that involves transformations of three variables, but planar just means that we're dealing with two variables. So you can see that, yes, G and R are subsets of R2, right? These are different coordinate planes, basically. You can think of them as living in different spaces altogether, although they're both still some version of R2. And you have a transformation mapping from one to the other, basically. Now we're just describing things a little bit further. So x you can think of as a function of u and v. X can be the x coordinate can be gotten from as a function of u and v, and y as well can be gotten as a function of u and v, and these are given different names, g and h. And sometimes it may be that the g and h we won't pick different variable names for them. Instead, we'll just use the same name as the letter itself, so that we think of the x as a function of u and v and y as a function of u and v. Although the book tries to use different letters, G and H in this case. So there's an assumption about this kind of transformation, which the book discusses, which is that the first partial derivatives are assumed to be continuous. Now, this is a nice property to have. I believe what it does is it allows you to define the Jacobian properly, because the Jacobian is described in terms of these first partial derivatives. And intuitively, the idea is that you want you want the transformation to act smoothly, going from G to R. You want it to not suddenly make creases in your space. You want things to um, smoothly map from one thing to another. And so that's what the idea of the partial derivatives being continuous represents intuitively. There's one, that is not the right, that's weird. What is that supposed to be? I think that's just a typo. T going from G to R is what it should say. I'll just say T going from G to R. So there's one thing in the homework that asks you to determine whether a given transformation is one-to-one or not. So you need to know what the term one-to-one is, and so that's what this definition is here. So being one-to-one just means that your mapping, it doesn't send 2 points in the domain to the same point in the image. So if you had it such that if you had like 2 points in G that map to the same point in R, then T would not be one-to-one. In order to be one-to-one, all distinct points must be mapped to distinct points. You can't have this kind of clashing happening. This is kind of a technical condition. Usually what it's used for, that you'll see in lower math, is that 1-to-1 is what allows you to define the inverse function, right? The defining the inverse function. The inverse function is only well defined if the function that you started with is 1-to-1. So like I guess as a simple example, the function of squaring, right? This y is equal to x squared. It doesn't have a well-defined inverse over the entire real number line. But if you take a segment of it, if you specifically take the portion from 0 to infinity, let's say, right, then that part you can invert, and that can give you the square root function. Okay, so you can see that the notion of being 1-to-1 depends on both the function itself, like the definition of the mapping, as well as the domain that you're talking about, which in this notation is denoted by g. So here, if we think of this function, if we think of the domain g as being the entire real number line, then this map is not 1-to-1. But if instead g is from 0 to infinity, then the function is 1-to-1, and you can construct the inverse from that. Okay, so now for this. So I created this to be very similar to your homework exercise. So suppose you have a map that is defined like this, where x, how do I want to say this? I kind of want to say that t sends you from uv to u squared comma v squared is one way you can denote this. So this is the x value, this is the y value. So we're going from the uv plane to the xy plane. Okay, that's what this is doing. And we're asked to determine whether this transformation is 1-to-1 on this set S, where, okay, since I'm using S, let me change this to S, mapping from S to R. So S is this triangle given by these vertices. So instinctively, what I would do is I would start actually by drawing what this looks like. Minus 3, comma 0 to 3, comma 0, and 0, comma 3. Okay, so it ends up being this triangle. Now, it turns out you don't really need to do that much work for this, because trying out these vertices will give you a clash that occurs. This doesn't have to happen in general. It could be that a clash happens within the region, but I gave you something nice. Your homework also gives you something nice. So what you can notice is if you actually map the point minus 3 comma 0 as well as the point 3 comma 0 under this, what it does is both of these points will get mapped to the point 9 comma 0. Right? You square the x coordinate, you square the y coordinate, or I guess you square the u coordinate to get the x coordinate. You square the the v coordinate to get the y coordinate. So in both instances, they both will map to 9 comma 0. That so two distinct points got sent to the same point in the image. That's not good. That is not being 1-to-1. So we can conclude that this mapping T is not 1-to-1, right, by this property. It's actually always going to be harder to show 1-to-1ness. If you want to argue that a function is 1-to-1, you have to argue that all distinct points will get mapped to distinct things. So that is a harder thing to show, and I think usually you're not going to be given that. So disproving 1-to-1 is easy because you just need a counterexample. You just need to find 2 points that get mapped to the same point. But if you want to prove 1-to-1ness, you actually need to show basically a for all statement, which is considerably stronger of a thing to show. And I would suspect that it's not going to show up. Although maybe I'll make one little comment about that. So you want to show one-to-oneness, what mathematically has to happen to show one-to-one? What has to happen is it ends up usually being a very algebraic kind of proof statement. So like it's that uh okay, if I'm trying to use the same exact notation here, then let me use t and I'm doing that. Yeah, so maybe I shouldn't be using xy. Maybe I should be using u and v because this is before we map over. Yes. So before we map over to the xy plane, we're in the uv plane. It's somewhat important to keep track of this, which coordinate system we're working in. There'll be a technicality later that we will need to discuss. So I'm trying to be careful and specify things. So t sends you from the uv plane to the xy plane. So it takes input that is in the uv plane. So something like this makes sense. And as output, this will be some x1 comma y1 and x2 comma y2. That is what will be the output of t. So the way that showing one-to-oneness would happen is you show that this statement must imply that the original points you start out with were identical. And so hopefully you can see that this is far too mathematical for for you guys in Calc 3. Proving things like this is much more, well, it's fine for math majors, but not so fine for engineers, right? This kind of statement. This is how you would show a map is one-to-one on a domain. It would be showing that this equality implies this equality, right? Meaning that if any 2 points got mapped to the same thing under T, it had to have been that the original points you started out with were the same point. So that's this statement, and yeah, and we don't need to go into any further because you're probably going to be showing something is not one-to-one, which only requires finding a counterexample, finding 2 points that get mapped to the same point, thus violating one-to-oneness. Okay, let's continue. So I just wanted to bring this graphic up. So this is a way to think about the polar transformation, right? The transformation from the polar coordinate system to the Cartesian coordinate system. But you'll notice that this is not the same as how we've been thinking about polar, the polar coordinate system. Because notice that in this image, the polar coordinate system is actually written as a Cartesian plane that has axes that are r and theta. Okay, so that is quite different. We're used to thinking of it as though r and theta live inside of the xy plane. But we're going to be thinking about things quite differently for this section because we're thinking about two separate spaces, but having a transformation between these spaces, mapping one space, quote unquote, into another space. Right? We're mapping like the r theta space into the xy space, and then what happens is that we end up getting this kind of distorted grid system. What you can see also, just let me relate this to the whole one-to-oneness of things. Theta here can extend up infinitely, right, in both directions. But if we were to do so, then the function will violate being one-to-one. We can at most have theta, we can have a block of theta running from, say, 0 to 2 pi. So something that is of length 2 pi. of height 2 pi, I would say. Like a rectangle of height 2 pi is possible, and that'll do is that'll wrap around the origin an entire revolution. But any more than that will make it so that the domain will violate being 1-to-1. Okay, as long as the height of this rectangle is less than 2 pi, the mapping is 1-to-1. Okay, not sure if there's anything else I want to say about this. Yeah, I think that's fine. Okay, so then moving on to the Jacobian. So these conditions that you have, so G and H are the transformations for the X and Y. So the X coordinate is defined to be this function G that takes in U and V, and Y is the function H that takes in the variables U and V. So these maps are assumed to have first partial derivatives that are continuous. I think I've duplicated what I said here. Each component function must have continuous first partial. Oh yeah, no, I am just restating it. But saying continuous first partial derivatives is sort of mathematical jargon. It means that you have, first of all, that you have the first partial derivatives, and second of all, that they are continuous. Okay, so this entire phrase actually means basically two things. This phrase means this phrase. And that has this property. So a transformation that has this property is called a C1 transformation. So just as a comment, C1, the C in C1 means continuous. The 1 means differentiable of order 1. So you can take the first derivative and the resulting function is continuous. So C1 really just means continuous first partial derivatives. So just to kind of extend what this terminology means, if you had C2, that means that you have the second partial derivatives and that they would be continuous. All right, so C1 means that you have first partial derivatives and those functions are continuous. Okay, given all of that, let's see, the Jacobian of a C1 transformation T, which is what we've been working with, this is defined to be this symbol, J, which there's a few other notations as well. So I'm also going to use the notation. I think I write it immediately below. Yeah. So I am going to use this notation for, I think, a few of the examples that I work through. So, but it's pretty clear. This is Jacobian of the transformation T, whereas here we're talking about Jacobian, and we're thinking of it as a function of two variables, u and v, which it certainly can be represented in that way because this ends up being expressed as partial derivatives. So, okay, first let me talk about this. So there's this notation. Actually, the book says this, but then it basically conflates things a little bit. I'm going to actually strike this out. The book says this, and I think even the online version says this, but what more commonly shows up in textbooks, I believe, is this version without the bars. So what ends up happening is that in the integral formulas, you end up having this with bars, where the bars actually mean absolute value. And then I'll make a technical aside about this later on, but it is convenient to have this represented as Jacobian so that you can have this with bars representing take the absolute value of the Jacobian. Okay, but this guy is supposed to be a matrix, and you can see that this can be thought of in this way, where you have the denominator, the derivative you're taking with respect to being constant in the rows, and the function you're taking derivative with respect to constant in the columns. So like x's are here, y's are there, whereas u's are here and v's are there. You can have it that way. And this is a 2 by 2 determinant, so of course you do main diagonal minus anti-diagonal to expand this out. And then thinking about this, x and y, well, this is x, and this is y. So x and y are functions of u and v, and so this entire expression is in terms of u and v, which is why we can think of the Jacobian as a function in terms of u and v, whose specific value will depend on what point in space you are plugging into the Jacobian. Part of the intuition here, which I'll state later, is actually that the Jacobian measures the amount of distortion of a unit square or unit volume. Unit volume, if you are talking about three-dimensional transformations, like transformations of three-dimensional space. Right now we're only talking about transformations of two-dimensional space. So the Jacobian in this case is measuring the distortion of area under the transformation. And so that distortion of area can depend on where you are in space. I think that's kind of clear from, well, yeah, it's clear from this picture, right? It depends on where you are in space, because if I go further in the r direction, I see that like I am distorting space even more. I'm making it larger and larger from here to, from like a unit square here, it will map to a much larger unit square in the xy plane. Okay. So Jacobian is right. Okay. Now we have this other remark. So this helps with needing to memorize things, I suppose. The point is that you don't have to remember the order of things here, because you have this nice property about determinants and matrices, which is that the transpose of a matrix has the same determinant as the original matrix itself, so the transpose, if you're not familiar with that terminology, that's what happens when you take a matrix and you flip it about the main diagonal. So if I notice that this matrix and this matrix are slightly different, okay, if I reflect about the main diagonal, I end up swapping these two entries, and that'll give me this. So this matrix and this matrix are actually transposes of each other. When you take the determinant of a transpose, and mathematically there's a few different ways of notating what it notating the transpose of a matrix. I'm using the quickest one, which is like putting a t as sort of like a superscript above the matrix. So this means A transpose. You take A and you transpose it, and you take the determinant. So the determinant of A transpose is equal to the determinant of A, right? So just flipping the entries of a matrix about the main diagonal, transposing the matrix, does not change the determinant calculation whatsoever. That's a general fact about matrices and determinants. So what that allows us to do is we don't need to remember precisely how this notation expands out for the Jacobian. We can write it in this way, where the partial derivatives are the same in the rows, or we can write it this way, where the function we're taking the derivatives of is the same in the row. And this is probably more comfortable for us to do, because this is most like, what is it called? Well, this feels very similar to the, is it the gradient? With the gradient, we took all of the partial derivatives of a particular function. So it's like we're taking multiple gradients, right? We're taking the gradient of x, we're taking the gradient of y in this, and we're sort of combining it all together into a matrix. Yeah. Okay. And yeah, so you can see that if you actually expand out the matrix, well, the determinant definition, you get exactly the same expression here. The only thing that changes is that the two factors here switch places in the anti-diagonal, but of course the multiplication is commutative, so these expressions are the same. Okay. And yes, I will use this notation to some extent. Okay. Um, Sort of a brief sanity check of our previous things that we've done is this calculation. So this is just to show or to prove to ourselves why it was that in polar we had that r showing up. Right? Why did I call that the Jacobian a few sections ago? Well, it's because you can really view the polar coordinate system integrating under the polar coordinate system as being this kind of this process of having this kind of transformation from the r theta plane to the xy plane, where you then have to factor in the Jacobian here. So, right, so under this transformation, the r theta, going from the r theta plane to the xy plane, we would then have to compute the Jacobian of this transformation, which when you expand that out, I'm using this convention. So, uh, partials of x here, partials of y there. So if you take when you compute out the partials, you can check this for yourself. You'll get this, right, for each of these entries. And then, of course, when you do the determinant calculation, you get r cosine squared plus r sine squared, and then factor out the r, and that simplifies to give you just r. Uh, and so we'll tie this into the actual conversion between integrals in different coordinate systems in this section. But let me just give you an example that looks a little bit closer to your homework problem. So the primary reason for this is that hold on, I think this should be a squared. Yeah, that should be a squared. So the primary difference here is that I wanted something that involved u and v instead of r and theta, just to not confuse people. So here we have this mapping that goes from the UV plane to the XY plane, and it looks like I'm pretty much copying a textbook example. So you can see that under this transformation, well, the main thing that it does is that it will transform this triangular region into this parabolic region. So if we're sort of thinking a little bit ahead, what we're really trying to do with this is that we would originally have an integral that is in the xy plane that is, say, over this region, this parabolic region, which is not so easy to integrate over. And it can be done, but it's maybe a little bit more involved. But under this transformation, and then knowing a fact that we'll shortly discover, we can integrate instead over the UV plane. What you can integrate over this region, this triangular region in the UV plane, which is certainly a much easier region to integrate over. And so what will need to be done, sort of previewing things ahead, is that the function will have to be converted over to the UV plane, and then the Jacobian will be needed to be factored in order to account for the difference in area between the UV coordinate system and the XY coordinate system, which is gotten by, well, understanding the way that the mapping T transforms areas of regions. Okay, so sorry that I'm sort of all over the place with my explanation. I guess this material is kind of involved. So the Jacobian of this transformation. So it's a straight up computation, right? So we compute the Jacobian of this transformation, which ends up being this matrix. So the partials of x with respect to u and v will be 2u and minus 2v. The partials of the function y with respect to u and v are going to be v for the u partial and u for the v partial. Yeah. Got to be a little bit careful about those letters. Okay, and then, well, computing that determinant, you get main diagonal minus anti-diagonal, which gives you this quantity. Okay, so that's computing the Jacobian. It's just the algebra after you take the partial derivatives, so it shouldn't be such a big deal. What's going to be a bit harder is wrapping your head around the transformation. Okay. So first, a little mention of this. The book tries to go into like a lot of details explaining how this stuff works in detail. I've decided to kind of skip over that. If you want to get more of a sense of how it works, I would recommend that you read the what the book says, this section of the book. You might have to start at the beginning of the section because I skip over quite a bit. But the main point is that indeed um so this description is kind of relating to this picture here. So you can see that in the UV coordinate system we have these kinds of rectangular pieces of area. But when we map them under the transformation t to get back to the xy coordinate system, we end up having some distortions on these rectangles. And in particular, this distortion can cause it so that they have different areas at different places in the xy plane. And that's what this is representing. So the change in the area in the xy plane ends up being related to the change in the u and v. So u and v are the sizes of these rectangles, and in the limit they're going to be differential elements. So it's going to be du dv instead of delta u delta v. But the main point is that you have this Jacobian factor showing up. This measures how much it's a multiplicative factor for how the area gets sort of scaled up or down when you transform it under t. So, right, you can see that from this. And so that's what the Jacobian measures. Okay. Now here's here's a very important theorem. So this is why we do all of this. So suppose that you have this transformation going from the UV plane to the XY plane. Okay. And just for the transformation to be good, we want it to be a one-to-one C1 transformation, right? So one-to-one meaning it's invertible, C1 meaning that the first partials exist and are continuous, so that the transformation is smooth, basically so the Jacobian is defined. So, and there's additional assumptions. The non-zero Jacobian on the interior, blah blah blah. That's fine. F is continuous. Those are all technical assumptions that don't really matter. What's important is understanding this formula. So, integrating this integral here is over the region R in the xy plane. So this is some complicated region R. This integral is over the UV plane, integrating over the region S, which is supposed to be some simple region to integrate over. Okay, and you can see that what happens is that the function f has to be transformed over in some way so that you can view it as being a function of u and v instead of x and y. And the way that's going to work is the transformation the transformation t will give you a function for x dependent on u and v, and y dependent on u and v, and so you just end up inserting them into the function f, okay, which you can see there. And then you have this Jacobian, right? And this Jacobian is measuring how much you need to distort the rectangular regions in the UV plane in order to get them to correspond to regions in the XY plane. Okay, so this is sort of correcting the distortion under T, correcting the distortion so that the areas of the regions match up, so that these two integrals are equal. Right. So having this theorem for double integrals, we are then able to do an integral over a complicated region in the xv plane by instead considering the region, or by instead considering the integral over the uv plane over a region that is simple to integrate over. Right? That's the takeaway of this theorem. That's what this theorem allows us to do. Yeah. Right. But so when we do this, we have to transform the function. We have to compute the Jacobian and take its absolute value, and we have to convert we have to determine what the domain S is in the UV plane and set up the integral in the UV plane instead of the XY plane. So there's a few things that we need to do in order to set up the integral to properly integrate over the UV plane. Okay, and we'll see examples of that. But before, I want to clarify a few. I guess these are technicalities going on. The book seems to gloss over it, and I know that students will find this a bit confusing. I find this a bit confusing. So first of all, there's something going on with the inverse transformation that the book sort of introduces but doesn't really introduce. The book tries to gloss over this, and it sort of overly it makes the book's examples a bit confusing to follow. So first, let's really understand that the transformation T is supposed to go from this easy region in the UV plane and map it over to this complicated region in the XY plane. And the whole point of this is that we start with an integral in the XY plane, but we want our integral to be easy to compute over the UV plane. Okay. So it's like we start over here and we end up wanting to kind of convert our way back here. But the map that we have is this map T going from UV to XY. Okay, that is our setup. Now, what the book seems to do in its examples, and this also shows up in the homework exercises, is that it defines the transformation the other way around. It ends up defining transformations x equals some function of u and v, and y equals some function of u and v. And if you think about what that means, that's actually the other way around. Or I might be stating it the wrong way around, actually. Let me see. I'm pretty sure. So it's like this. Okay, yeah, so I think I said it the wrong way around. It gives you transformations. U is some function of x and y, and v equals some function of x and y. So it really is completely the opposite order. So if you think about like how this transformation works, this is taking in inputs in the xy plane and giving you back outputs in the uv plane. So this description is actually a description of the inverse transformation of T inverse. And I can even diagram that here. T inverse going from the xy plane to the uv plane. Now, there is a reason for this. There is a reason why the book is doing this, which is that it's easier, or it's more natural that you'd be given a problem in the xy plane. Like, our original problem is starting in the xy plane, and it's some complicated looking region. And the point is that if you aren't given the transformation, if you know, whoever's assigning you problems, if they aren't nice, they would just give you some complicated region and not even tell you what the transformation is, and you'd have to create the transformation yourself. And that might be kind of tricky. But it would be easier to think about it as taking this complicated region and figuring out a way to map it to being nice. Creating this map from XY that is complicated to UV that is simple. Creating this transformation is easier to construct by hand rather than thinking about how you would go the other way around. So that is why the book gives you the inverse transformation. It's because it's easier to naturally come up with as a way to sort of straighten out the curvy space here to make it more rectilinear. But, and then I'm sort of trying to paraphrase what I've written here. So that's why this process, that's why the inverse transformation shows up. Right? It's easier to construct by hand. But this theorem requires t, not t inverse. You need the transformation going this way. So to rectify this problem, what the book does is it then says a few things in its examples about how you invert that map, right? So you ended up with a transformation that was t inverse, and you have to invert that in order to get the transformation t, which is basically solving a system of equations for the other collection of variables. So I do end up doing that for the examples that I'm showing. But I want to actually make a bit of a comment about this. So yeah, so the book's process is that after you have T inverse, you then construct the inverse of that map, which would be T, and then you would compute the Jacobian of T, which would be this quantity here. Yeah. And, well, there is actually an easier way of computing this quantity if you don't need the transformation T itself, which, at least in the examples, it doesn't seem like you do need T itself. You just need to know where the region is, but going from this region to that region, you can do that using T inverse. So you can figure out what this region S is without using T. And the property is this. So the Jacobian of the transformation T is related to the Jacobian of the inverse transformation of T as being the reciprocal. So I'm sort of overloading what this -1 superscript is doing. Here, the -1 means inverse transformation. Here, the -1 means negative first power, means reciprocal. So I've written it again in this format. So this is how the Jacobian is related to the Jacobian of T is related to the Jacobian of the inverse transform T inverse. Right. So they're you can compute Jacobian of T by just computing Jacobian of T inverse, which would be more natural if you're just given the mapping T inverse. You can compute that and then reciprocate it, and that is going to be the Jacobian of T, which is actually what you need to insert into the formula. So in my examples, I'm actually going to show you both ways, and you can take your pick. I think it's more. I suppose it depends on who's teaching it, but since I'm teaching it, you can choose whichever approach you want to do. May as well be versed in both approaches. Why not? Okay. So that's one of the remarks that I wanted to make. This mapping direction is important to pay attention to, whether you're working with T or T inverse, right? Whether you're mapping from nice space to complicated space or the other way. What you want is the mapping from UV to XY, nice to complicated, instead of the other way. So, okay, and then there's another comment. So this is a much more technical aside, I think, which so the Jacobian itself can be negative, right? Notice that in the definition of Jacobian, we were talking about the determinant of a 2 by 2 matrix, and the determinant is a number. It can certainly be negative, right? Well, over here it's related to R. R can be negative, or just this product. So that quantity can be negative. The Jacobian being negative means something about the transformation geometrically. It means that the transformation is reversing the orientation of things. So, so like what ends up happening in I guess I can relate it to the bottom example. What happens in this example is that okay, I guess I'll just sort of diagram it here. Actually, it's kind of so I'm already kind of doing the wrong thing. So I'll say T inverse. This ends up mapping to a square, but the orientation of the square is the reverse. I believe it's this way and then up. So if you sort of parameterize the points of this region, you would end up going in counterclockwise fashion, whereas if you map these points over under this transformation to the UV plane, what ends up happening is that this ends up parameterizing the region, which is a square, in the reverse orientation. So that is what I mean when I say that the transformation can reverse orientation. It's this kind of technical thing that happens. Um, and so I'm underlining this main thing, which the book doesn't make clear, which is that in the integral formula, so this formula here, these absolute value, these bars mean absolute value, or they should mean absolute value. The book makes it unclear because it also kind of says that this notation can also mean just the Jacobian itself, which could be negative. I'm telling you, no, it should be positive. So the reason that this works out fine is because when your transformation has this orientation reversing property, there ends up being two negatives that arise in the integral formula, right? In this integral formula. The first negative is clearly coming from this Jacobian, okay? So if you didn't have the absolute values, you'd have a negative here, but you'd have another negative showing up in what is the more technically correct way of setting up this double integral in S, which is that you, how do I say this? You would fix the orientation. You would make the orientation around R depend on the orientation around S. And so if, say, you went from this point here to this point, if you went in this direction, but the transformation ended up going from this point to this point, but in the opposite direction, the integral would also carry the correct, it would carry the analogous kind of ordering of the variables. So it's like moving in positive x ends up transforming in negative u instead. And so in this double integral, instead of, say, u going from 2 to 5, you would have u going from 5 to 2. And so that ends up picking up another negative. Is the other negative shows up in the way that you parameterize this double integral. So if the transformation is orientation reversing, two negatives arise, one in the Jacobian, one in the parameterization of the double integral of S. And so these two negatives will cancel each other out. So a simpler way of viewing this whole thing is plop absolute values around the Jacobian and take your integral in the standard way that you'd set up the integral in S. You'd make it so that all the things are oriented positively, so that when you integrate with respect to u, it's done positively, and when you integrate with respect to v, it's done positively. That gets rid of this orientation concern, right? So because the two negatives will cancel, and so we can sort of cancel them out and make it so that we can think of it in that way. Okay. Now the book doesn't describe it in that way. I don't know why. I think this description makes a lot more sense. Okay. Now for examples. So these two examples that I'm going to show you, they are really similar to your homework. So unfortunately, I don't have the time to change the transformation itself and to come up with completely different looking problems. So I've actually opted to use the same transformation and just change the function that the integral is supposed to be over. It's going to be up to you to make sure that you understand the whole process of doing the calculation for a given transformation. So make sure that you don't just skip over this and copy like what I've done. Like make sure you understand how I'm doing this. So in this example, we're given this transformation, and I'm telling you that this is the integral we want to compute. The region that we're transforming is this parallelogram with specified vertices. Okay, and so the first thing I would do is so this parallelogram R is in the xy plane. I would plug in all of the points. I would map all of these points under this transformation. And yeah, just as a comment, this is what's defining T inverse. Right, T inverse going from x comma y and mapping you to u comma v. Mapping you from some region R to some region S. Okay, so I want to see what S looks like in order to set up my integral. I'm also going to need to compute the Jacobian, but that's not too bad. That's pretty simple. I want to figure out what this region is. So what I do is I take these 4 points that define the parallelogram, and I map them under the inverse transformation, this T inverse. So you can do that, and just kind of quickly run through that calculation, and you'll get these 4 points. And then, of course, you would plot these 4 points, which I do below. You end up with this rectangle. Well, it's a square. But you have an opposite orientation. So notice, like, going from 0, 0 to, say, 1, 0, this is, and then what, to 2, 1, right? So these 3 go in this order. But if we look at these points, that's 0, 0 to minus 1, 0, minus 1, 1. So 0, 0, minus 1, 0 to minus 1, 1 ends up being exactly this parameterization. So there's an opposite, this transformation reverses the orientation. Okay. Now, computing the Jacobian. So I'm going to do this in both ways. The faster way that I showed, and also the textbook way. So the faster way is that we use the transformation T inverse that's given to us. So, okay, I actually have it copied down here. So this ends up being the transformation T inverse, and this is the transformation T. Maybe I'll even, maybe I'll label them. So this is T inverse, and this is T. Okay. It's a bit hard to label this. T inverse is this guy, and T is this guy. So if you take the partial derivatives with respect, the partial derivatives of u and v with respect to x and y, you take the Jacobian of this, you get this matrix. You can check that for yourself. It should be fairly quick. And then computing the determinant, you get minus 1. That was the Jacobian of the inverse transformation. We want the Jacobian of the transformation, so what we do is we reciprocate this guy, which gives us minus 1. Okay, so that's the fast way to do it. The textbook way of doing it is that you start with this inverse transformation, and you need to solve for the inverse of this inverse transformation, which would just be the transformation T. For this, it's not so bad. Notice that y equals v, you can swap these two, and you get that. And then for this, you solve for x, and when you do that, I think of moving x to the other side, move the u to the other side. That gives you x is equal to y minus u, and we showed that y is equal to v, so of course that gives you v minus u. That's how we end up with the first equation there. So this is the inverse of T inverse, which is T. This maps you from uv to xy, which is what you want. Computing the Jacobian of this, we get, well, so it ends up being this determinant, and then you can kind of quickly check these 4 partial derivatives, and taking the determinant gives you this quantity. So notice that both of these are the same, so that's good. Everything checks out. And now, what we're supposed to do, what a problem told us to do, was to convert over this expression, I really hope I did change that expression. Yeah, marginally. I changed it a little bit. Okay, yeah, good enough. All right, so you'll notice that so x minus y is the quantity u, and y is the quantity v. We have to convert our function that is in the xy plane over to the uv plane. So that conversion is pretty straightforward because the function is written in terms of things that look like u and v already. So we can convert that over. But as we convert our integral from the xy plane to the uv plane, we have to factor in the Jacobian, and we have to integrate over a different region, S. So S is this rectangular region. I sort of define it here. It's the image of R under the inverse transformation. Okay. Right, and so absolute value of the Jacobian, which is the absolute value of -1, which is going to disappear like in the next line. Integrating over this rectangle, you can do it u first or v first. Right? So I decide to integrate first with respect to u, then v. Going with this, integrating with respect to u, we go from -1 to 0. I'm just going to do it in the standard order in the uv plane. So where u is oriented positively and v is oriented positively, which means u goes from -1 to 1, v goes from -1 to 0, or from v goes from 0 to 1. So that gives you these bounds, u from -1 to 0, v from 0 to 1. You have this function, and then, well, the absolute value -1 is going to disappear. This is a product of two functions u and v, so we can split it into a product of two integrals, especially because this is a rectangular domain, right? So splitting this into the two different integrals, we have the integral with respect to u. The bounds follow from the bounds for the integral of u. The bounds for v also follow for the integral for v. And then you just proceed to integrate and you get the answer. Not too bad. After all the transformation stuff. Okay. Yeah. And this next example, this is also similar to your homework. So yeah, again, I'm using the same transformation, using the same region. I've just changed the function. This is the region, or this is the transformation itself. This is the region R. And so what you can reason about is that this takes the input in x and y and returns you a point in uv. So this is, again, T inverse. This is going from x comma y and mapping you over to u comma v. Not the other way around. So we have T inverse given to us. And then what we do is the same as the previous example. We take these 4 points and we want to see what the image is under the T inverse map. We want to see what the domain S is in the UV plane. So we apply T inverse to all 4 of these points, and if we do so, you can check the computation yourself, and you'll get these 4 points. And then when you visualize this, so you just sketch this region out, you get this. Well, this this region is not too bad to integrate over. Hopefully that's fairly clear to you. This region is going to force an integration order on you. I mean, unless you want to split it up into 3 integrals, then I would say that you shouldn't want to do that. The integration order is you have u on the outside, and then the integral for v depends on u. This is a line of slope -1. This is a line of slope 1. So the way that you define this kind of integral is, if I just do this off to the side here, I do it below, but let me just sort of mention it here. So the way you'd integrate over this region is u, you'd go from 1 to 2. That's pretty clear. And then for v, you want to notice that at 1, this is the value -1, and then at 2, the value -2. this is captured by the function minus u, right? It's the line negative u, slope -1, passing through the origin. And then the upper bound, this upper function, this is captured by the equation v equals u. So you have that. And then this is whatever the function is, f, let's call it. Okay. And I guess technically I should put the Jacobian here, so maybe I'll say the Jacobian of t in absolute values, dv du. So this is the integral that integrates over this region. Okay, let's come back to the Jacobian calculation because that's what I write next. Right. So again, I have t inverse written as well as t. So if we do this the fast way, we would take the Jacobian from the inverse transformation and then reciprocate it. So you can check that the Jacobian of the inverse transformation is going to be this determinant. Computing each of the values, and then computing the determinant gives you -2. Reciprocating gives you -1/2, which is then the determinant for, or the Jacobian for the transformation t. If you do it the textbook way, what you would do is you would solve for the inverse transformation to this transformation. So you want a function for x that depends on u and v, and you want a function for y that depends on u and v. The way that you think about this, if you're not already familiar with this, is you solve the system of equations for the other collection of variables. So notice that you have a nice property that shows up. If I add the two equations here, if I add these two equations, well, the left-hand side gives me u plus v. The right-hand side gives me 2x, right? The y's cancel. So we have 2x is equal to u plus v. Dividing by 2, we get x is equal to 1/2 u plus v, which is the first part of our inverse transformation. If instead we subtract the two equations, that will cancel the x's and that will double up the y's. So we will have 2y is equal to u minus v. Dividing by 2 gives us this equation. So that's how we end up solving for the inverse transformation given this. I think of this as just linear algebra. If you're not familiar with that, then that doesn't help. So, but it's about solving this system of equations. There are ways to, if x and y had like some random numbers in front of them, there would always be a way to properly scale the two equations to get rid of the y's and then dividing by whatever constant is in front of the x's. And then similarly, there'd be a way to cancel the x's and only be left with the y's, and then dividing over, well, I'll do the same thing. So I believe the book has a more complicated example that shows this, where the transformation doesn't have just ones and minus ones, but it has like other numbers here. So you might check that. Either way, so once we have this transformation t, then we can compute the Jacobian for t directly from this transformation. You take the partials of x and y with respect to u and v, populating this determinant, computing it, and then taking the determinant gives you this. So you end up with the same quantity. Very good. Okay, now this problem is a little bit harder to integrate. So starting off, we had this. And I purposely made it so that the function is close to your function. I made mine a little bit worse than yours, just to illustrate things. So when we convert the function to the uv plane, notice that x minus y is v, so this ends up being v to the fourth, and x plus y is u, so we have e to the u. And then we have the Jacobian, we have a double integral over s. This integral is happening in the uv plane now, whereas this was in the xy plane. And you'll notice that these bounds are the same as what I described here in order to integrate over this trapezoid. We have, that's kind of hard to read what I've written here. The outer integral u goes from 1 to 2. The inner integral is v goes from minus u to u. Yeah. The Jacobian was negative 1/2. We put that in absolute values, and we have this function. Okay, so the 1/2, I can pull that out all the way. That's not too bad. And then the next thing I focus on is, so notice that this we have to treat as an iterated integral because the bounds here aren't, this is not a rectangular domain. The bounds for the integral with respect to v depends on the value of u. So we have this coupling between v and u. So we can't just split these things apart. We have to treat this as an iterated integral. What we can do to simplify the integration is this function e to the u is treated as constant with respect to this integration by v. So you can imagine pulling this factor. This is like a multiplicative factor for the integration by v. So we can pull it out of this integral. This v integral only integrates the function v to the 4th. And so that's why we end up getting v to the 5/5, which we then evaluate from v equals minus u to v equals u. Okay, so we end up with this as our next step after we do the inner integral. Doing the evaluation, both terms are going to give you a u to the 5th. This one gives you u to the 5th. This one is going to give you a minus u to the 5th, which is subtracted because that's the second part of the evaluation. So we have two negatives, which gives you a positive, and so you actually have a total of 2/5 u to the 5th. That 2 is going to cancel with the 1/2 outside. The 5 is going to be pulled out. That's why we end up with 1/5 here. And then we have u to the 5th, e to the u, du, integrate from 1 to 2. Okay, and now this is where this would be a pain if you didn't know tabular integration. So, if you didn't know tabular integration, this specific integral, you would have to do integration by parts 5 times to reduce it down all the way to e to the u. But with tabular integration, I don't really want to spell out exactly how this process works because that is a lecture in it of itself. I'll just mention that I've written that, so your problem is also going to use tabular integration. Oh, it will be beneficial to know how to do tabular integration. If you don't, then you would have to do integration by parts 3 times for your specific problem. So if you're not already familiar with tabular integration, also called the DI method, you should search on YouTube this phrase. So BPRP, that's Black Pen Red Pen. He's a YouTuber. He explains Calc 2 concepts really well, and in particular, he has like popularized the DI method, or at least this way of calling it. So textbooks will call it the tabular approach, or the tabular integration by parts. So if you're not comfortable with this process, maybe take a look at some of those videos. He has multiple videos on this topic. He's kind of gone through it over the years. It's helpful having this method in your arsenal is helpful because otherwise, yeah, you would take a very long time to do what I'm about to do. Right, so I think I need a little bit more space than that. So I'm going to start all the way up here. I'm setting up columns D and I. I have a column that I differentiate, which is going to be the function u to the 5th. And I'm going to integrate the function e to the u, and I'm going to do that multiple times. So the real power of this DI method is when you are differentiating. If you're doing integration by parts over and over and over again, where you're differentiating the same part of the function, of the integrand. So in this case, we are differentiating u to the 5th 5 times to bring it all the way down to a number. And so this is where the DI method really shines. If I take the derivatives 5 times, let's see, we get 20 u to the third, 60 u squared, 120 u, 120, and I'm going to do it one more time to give me 0. On the other column, well, we have this nice thing where integrating e to the u is always the same. So for completeness sake, I will write it multiple times, but I don't really need to. It's only necessary if, say, the problem could be made worse if over here, like you had a negative times the whole thing, or you maybe had like a -2 or something. If you had some number in front of here, integrating this will make the number keep popping up as a coefficient, and so then that would be necessary. Next part of the DI method is the way that you read off the answer. So we have a sign column as well. I'm introducing that. So there's a sign column, the signs alternate, and the result of the integration by parts is read off of the diagonals. Each diagonal, including the sign, is a term in the final result of the integration. If you don't end up with a 0 row, then the last row that you end up doing that is reasonable to do, the last row would be interpreted as an integral. It would be the integral of u dv equals uv minus integral v du. That integral v du at the very end of the integration by parts, that would be this bottom row. So you can always reinterpret the bottom row as an integral, but when your differentiation column has a 0, that final integral is the integral of 0, which is just a constant. So that ends up just being your constant of integration, and you can safely ignore it. There are other types of problems where you end up requiring that bottom row, but we don't have that here, so I'm going to not mention that. If you want to understand the DI method in full, you should look at Black Pen Red Pen's videos on it. And you'll see that there are 3 possible kinds of situations that can occur. This kind of terminating case, a cyclical case, and a sort of rejoining case. Okay, anyway. So, right, let's just read off that we actually do get this final result. So notice that all of the terms have e to the u, so I can factor that out. So I only need to really think about the signs next to these things. So u to the 5th minus 5u to the 4th plus u to the 3rd minus 60u squared plus 120u minus 120. Notice that that is exactly this polynomial here. And so that's how we got that. So we were able to do 5 integration by parts in just a table. That's the power of the DI method. All right. And now what we're supposed to do is evaluate this from u equals 1 to 2. Yeah, so I just did that on a computer. I didn't bother to do that by hand. I mean, you could. It's not impossible, but you know, it's just gonna be numbers, and you end up with that. Okay, fine. All right, so that's that example. Okay, and I think that I don't have. So the last bit of material that I've written here is just to kind of connect this topic with the spherical and cylindrical coordinates. So which lies in this section on change of variables when we have triple integrals. So what we did with transformations in 2-dimensional space can be extended to transformations in 3-dimensional space, which is what the book describes. I've more or less copied the important bits of what are stated in the book. So such a transformation takes in 3 variables, so it might go from a space UVW to a space XYZ, mapping in kind of the same direction, right? UV to XY, we have UVW to XYZ. Well, so the book is calling this capital F for some reason. And it's just describing it as another function. Uh, I think it's fine. What's important is like the Jacobian definitions. So you can see that I've written one of these is the transform of the other. So in this one we have the along the rows the derivative that we're taking, like the u derivative, the v derivative, the w derivative, are the same along the rows. Whereas in this one we have the transpose of it, where along that happens along the columns, whereas along the rows we have that we're integrate or that we're taking the derivative of the same function. The This is like the gradient of x, the gradient of y, the gradient of z. Okay. Right. So that's how the Jacobian works in 3 dimensions. And yes, you might see this kind of notation show up. Then we have an analogous version of the change of variables formula for triple integrals. This is similar to the one we had for double integrals. So again, we assume that this transformation t is 1 to 1 in C1. Additional kinds of assumptions. And the point is that we would have this integral of the function f over some region R that is complicated in the xyz plane. Well, I don't know if it's right to call it a plane. XYZ space is probably the better term, but the book apparently calls it the plane. So in this XYZ kind of space, you'd have this integral. Well, you can convert it over to being an integral, a triple integral, in the UVW space. What you do is, under this transformation, you end up having ways of expressing x, y, and z as functions of u, v, and w, which you then just insert in. This is exactly the same as what happened in the 2-dimensional case. And then you have the determinant of the Jacobian, right? But this time we have the 3-dimensional Jacobian instead of the 2-dimensional one. And then, of course, G is the nicer, hopefully nicer region to integrate over in the UVW space. And for whatever reason, the book just kind of renames this function f into some function h, maybe because it looks simpler, maybe just to make this expression look a bit simpler. Fine. Okay. And I think this last bit is the main thing that connects these two. This section with the previous section, the section on cylindrical and spherical coordinates. We can show the Jacobian, right? We can show why the Jacobian that was claimed in the previous section is the way that it is using these formulas. Okay, so in the cylindrical coordinates, well, cylindrical coordinates you can think of as a transformation from some space r theta z to the space x, y, z. In particular, that transformation uses this set of equations, which you can hopefully recognize. This is the equations that convert you from cylindrical to Cartesian. Right. Computing the Jacobian for these. So this isn't too bad. Maybe you can kind of quickly read it over and notice that you do end up getting this matrix. And then taking this determinant. So the way I would compute this is I would expand along, you can think of it as along the bottom row or along the last column. Plus, minus, plus, minus, plus. This one is treated with a plus, and so you have 1 multiplied by this subdeterminant. This subdeterminant is just going to be r cosine squared minus negative r sine squared. So it's r cosine squared plus r sine squared. That gives you this. And then, well, you factor the r out, and you have this cosine squared plus sine squared, which is simply 1. So you end up with r. So this shows you that the Jacobian for cylindrical is r, which agrees with the Jacobian for polar. Kind of expected. Okay, and so we end up with this as our final conclusion. So when we have an integral defined in Cartesian, we can rewrite it to be an integral in cylindrical, where we have to introduce R, we have to sort of redescribe our domain, and we have to convert our function over as well. And now this is the bothersome part, spherical. So this computation, I like to call it a once in your lifetime computation. You only want to do this computation once in your lifetime, and like never again. You maybe learn it the first time you maybe learn something from doing it the first time, but then any subsequent time that you do it, it's a slog, and you can go through it, but it's like you don't really learn anything. Okay, um, so the spherical coordinates, you can think of it as a transformation from a space rho theta phi to a space x y z. I'm gonna make a comment about this, which is that I think that this is not the right choice of the order. I think that this it's more sensible to use rho phi theta, because this order will actually give you a negative for the Jacobian, and then I have to kind of mention things about that. But if you actually flip the order of these two variables, phi and theta, that will flip the rows. Is it the rows? The columns, I think. That'll flip the columns. And flipping the columns is actually going to introduce a negative into the determinant. And so that corrects the negative that shows up in the Jacobian. But it's fine either way. So, okay. Anyway, so if we just sort of like, I'll just talk through the computation, and whether you want to actually like try working it out and checking all the details yourself or not, it's up to you. So first you have these 9 partial derivatives, and the transformation T mapping from spherical to Cartesian is given by these 3 equations, right? Which you should be able to see they are the formulas that convert you from spherical to Cartesian. You have to compute the partial derivatives of these, which is kind of a pain to think about, but you can do that. And if you do that, you should get this. Notice that what we'll want to do is to exploit the 0 here when we compute this 3 by 3 determinant. So what we can do is cofactor expand along the bottom row. Plus minus plus, this one is treated with a plus, and so is this. So there's no sign alternation with these cofactors. The something is already wrong here. Okay, I'm fairly sure that this 0 is supposed to be phi. Okay, I think I copied this straight from the book, so this might mean that the book has an error as well. Okay, so cosine phi. Right, so cosine phi is there, and then you have the subdeterminant given by these 4 entries, and then 0, and then this cofactor. So this one, this cofactor is going to give you this subdeterminant with these 4 entries, which should be here. Oh gosh, it looks like there's a... Yeah, I think there's definitely something wrong, but I really did just copy paste this, so it looks like there's a negative missing here. Okay, so maybe it's this entry. Let me think. Sorry. This is y theta. Y theta is positive. Yeah, it is positive. Rho sine. So with respect to rho gives you that. With respect to theta gives you that. With respect to phi gives you that. Rho gives you that. Theta gives you that. Yes. Phi gives you that. Yes. And then rho gives you that. Phi gives you that. Okay. Yeah, I think that's correct now. So this subdeterminant there, that subdeterminant there, that looks right. Then the next thing you do is expand out these 2 by 2 determinants, which is going to give you this for this submatrix, or for this subdeterminant, it's this, and for this subdeterminant is this. At first glance, I think that looks right. I'm trying not to carefully go through that. So then the next thing you do is factor out things in common. So over here we have a minus rho squared sine phi cosine phi, it looks like. In common, so that ends up doubling up the cosine phi for this term. And then you're just left with a sine squared plus cosine squared here, which the next thing is going to be to make that equal to 1. And then in this factor, you have a few things in common. You have a rho sine squared phi in common, which when you pull it out becomes this. And you're left with a cosine squared plus sine squared, which is going to just be 1 when we simplify. The next line simplifies that. Both of these become 1, so you end up with this. And then notice that this has a few things in common also. We have a minus rho squared sine phi in common, it looks like. So factoring that out, you get a cosine squared phi plus sine squared phi, and that is simply 1, and so you end up with this. So the Jacobian is this. And so if you recall the Jacobian spherical, it was rho squared sine phi. So this is pretty much the same as the Jacobian that we are familiar with for spherical. The only thing is that negative. So as you know with the, well, as I mentioned about this change of variables formula, we have a absolute values surrounding the Jacobian. So you could just think of it as getting rid of that get negative when you actually plug it into the conversion formula. Although I think some argument can be made that this is not the right ordering of the letters. It's a technicality that you don't need to really know about, but instead of rho phi theta, I think it should be rho theta phi. Or wait, no, I think, did I reverse it? Oh, no, no. So, yeah, this computation was done with rho theta phi. I think it should be done rho phi theta. Yeah, rho phi theta. D rho d phi d theta is the standard way that you would write an integral in spherical. So I believe that there's a reason for that, which is to do with the fact that that corrects the orientation error that shows up with this transformation. Okay, either way, we end up with this equation, which shows you that we can convert a triple integral in Cartesian into a triple integral in spherical, right? You have to convert the function itself, you have to convert the domain over, and you have to introduce the Jacobian, which is exactly what we saw in the previous section. So there we go. And yes, just final comment, homework hints. So I don't think that the first one is too difficult, but just in case, I gave that to you. And this one is a little bit bothersome, perhaps. And you're probably going to want to use tabular integration because you'll have to do. It's very similar to what I did. I think the main difference is this is not to the fourth. This is squared for you guys, and that will end up giving you an integral where you have v to the third power here. That ends up being a u to the third. Wait, v squared here, which ends up being a u to the third power here, if I remember correctly. So you'll have to do a shorter version of this, more or less. So have fun with that.